You're listening to the Bare Metal Cyber Prepcast, created to help you succeed in your educational journey. Learn more at baremetalcyber.com, where additional prepcasts, books, and training materials await. Let's get started. When we talk about secrets in code, we are really talking about the hidden values that allow software to connect, authenticate, or unlock critical resources. These values can be as simple as a password or as complex as a private encryption key. The purpose of eliminating hard-coded secrets is to protect both the integrity of applications and the systems they interact with. By removing these embedded values from source code and binaries, developers reduce the risk of leaks, unauthorized access, and downstream compromise. At the same time, organizations must provide a safe, reliable way to deliver sensitive values at both build time and runtime. That means adopting practices where secrets are governed, retrievable, and revocable without rewriting code. A shift toward secret-free applications is not just a security best practice, it is a fundamental requirement for resilient, trustworthy systems in a modern cyber environment. Hard-coded secrets are one of the most common and dangerous mistakes made in software development. A hard-coded secret is any sensitive value directly written into source files, compiled binaries, images, or even configuration templates. The problem is that once these secrets are baked into the code, they travel wherever the code goes. A developer's laptop, a build server, or even a public repository can all end up carrying the same embedded credential. Think of it like leaving your house keys taped under the doormat. You may know they are there, but so does anyone else who looks closely. Because of this portability, hard-coded secrets can spread far beyond their intended boundaries, putting both the codebase and the connected systems at risk. The types of secrets that typically get hard-coded are surprisingly diverse, but they all share one trait. They are meant to unlock something important. Passwords are the most obvious and remain the most frequently mishandled. Application Programming Interface keys, commonly shortened to API keys, are another major category, as they provide access to external services like payment systems or mapping engines. Tokens, which are temporary by design, often become permanent when copied into code. Finally, private keys, which should protect encrypted communications, can become devastating liabilities if exposed. Each of these represents a piece of digital identity, and when embedded in code, they create a permanent retrievable fingerprint that adversaries can exploit. Leaks of secrets can occur in ways that are often invisible to developers until it is too late. A public repository, for example, may seem harmless when created for experimentation, yet it can inadvertently contain sensitive credentials committed months earlier. Package registries, where developers publish reusable code, can spread a secret to thousands of users without warning. Crash dumps, which are automatically generated when programs fail, can capture memory contents, including passwords and tokens, and store them in plain text. Mobile bundles, like Android or iOS application packages, can also leak keys that were meant to remain internal. Even container layers, which stack up to form portable environments, can fossilize old secrets inside images that get reused for years. To counter these risks, developers rely on a practice known as externalization. Externalization means taking secrets out of code and relocating them to secure retrieval systems that are governed by policy. Instead of embedding a password in a script, a developer configures the application to request it at runtime from a vault. Instead of storing an API key inside a configuration file, the key is stored in an encrypted database accessible only under specific conditions. This approach does not eliminate the need for secrets, but it removes them from static places where they can easily be copied. The result is a shift from fragile, hard-coded values toward managed, revocable identities that align with the principle of least privilege. Even with externalization, it is critical to have safety nets in place. That is where secret scanning tools come into play. These are automated systems that analyze commits, repositories, and code artifacts for patterns that resemble sensitive values. For instance, they may detect a long alphanumeric string that matches the format of a cloud provider's API key. By running at commit time, Before code ever leaves a developer's machine, these tools act as an early warning system. They can flag high-confidence matches and alert the developer immediately, preventing contamination of the shared repository. The earlier a leak is caught, the cheaper and less disruptive it is to fix, making scanning an essential part of modern development hygiene. Secret scanning is most effective when combined with preventative measures built into the development workflow. Pre-commit hooks, for example, are scripts that run automatically before a change is committed to a repository. If the hook finds a potential secret, it blocks the commit and provides feedback to the developer. Similarly, checks integrated into continuous integration pipelines can halt a build if a secret is detected. These safeguards prevent vulnerable code from moving forward, reducing both accidental exposure and the time needed for remediation. It is the equivalent of a smoke alarm in a house, an alert system that stops small mistakes before they grow into damaging fires. A common way to deliver secrets safely is through environment variables. These are values provided by the system at runtime rather than embedded in the code itself. Environment variables can be convenient because they work across platforms and require no code changes. However, they must be handled carefully. Developers need to ensure that variables are masked so they are not accidentally printed in logs, scoped so they apply only where needed, and managed through a defined lifecycle. Without hygiene, environment variables can quickly become just another hiding place for secrets visible to more processes and users than intended. Proper governance makes the difference between a helpful delivery channel and a dangerous exposure point. As systems have moved toward containers and serverless functions, orchestrator-level secret management has become essential. Orchestrators such as Kubernetes can store secrets in encrypted form, bind them to specific workloads, and enforce retrieval policies. This means a containerized application no longer needs to carry a key inside its image. Instead, it requests the secret securely at runtime. Similarly, serverless platforms offer managed stores where secrets can be linked to function identities. These approaches reduce exposure by ensuring secrets are encrypted at rest, retrieved only under the right conditions, and logged in ways that support compliance. In practice, this transforms the application environment from a static set of files into a dynamic, policy-driven system. While orchestrators help manage runtime, build and template systems must also be hardened. A subtle but dangerous problem occurs when secrets are accidentally rendered into static artifacts, like configuration files, logs, or even templates that generate new environments. Once a secret makes its way into a template, every environment deployed from that template inherits the same vulnerability. Build pipelines must therefore be designed to strip out or prevent rendering of sensitive values. This involves careful review of what gets logged, what is written to disk, and how configuration is templated. The goal is to ensure that no secret survives long enough to be baked into the permanent record of an artifact. Another important layer of defense is encryption at rest. Even secrets stored outside of code must live somewhere, and that storage must be resilient against theft. Using a key management service or KMS allows organizations to encrypt secrets with managed keys that are themselves rotated and secured. In higher security environments, hardware security modules or HSMs provide tamper-resistant storage for cryptographic material. The point is not simply to encrypt, but to encrypt in a way that integrates with policies, audit logs, and automation. Properly managed encryption at rest ensures that even if a storage medium is stolen or compromised, the secrets remain unreadable without the authorized keys. Runtime retrieval of secrets is another practice that closes the door on static embedded credentials. Instead of embedding a long-lived API key in code, applications can use workload identity, a process where the runtime environment itself proves its identity to a secret store. In exchange, the store issues short-lived credentials that expire after a brief window. This model mirrors the way a hotel issues room keys. The card only works during your stay, and once the time is up, it becomes useless. By embracing identity-based retrieval and temporary credentials, organizations dramatically reduce the value of stolen secrets, since they expire quickly and cannot be reused. Managing the life cycle of secrets is not complete without rotation. Rotation policies define when and how secrets are renewed, ensuring they do not remain valid indefinitely. A rotation plan typically includes the format of new credentials, a notice period for systems to prepare, and an atomic cutover to avoid downtime. If a database password must change every 90 days, for example, automation can generate a new password, update all authorized clients, and revoke the old one without breaking connections. This process ensures that even if a secret is compromised, its window of usefulness is limited. Rotation transforms secrets from static risks into time-bound, renewable assets. Access scoping adds another layer of control by defining exactly who or what can read each secret. Instead of allowing all developers to access all keys, policies can restrict access by application, environment, or purpose. For example, a payment processing service in production may have permission to retrieve a payment API key, but a development environment does not. Similarly, one application may be authorized to read from a database, while another can only write. These distinctions help contain damage if an environment is breached, because the attacker only gains access to the limited secrets available in that scope. One of the easiest ways for secrets to leak is through logging. Logs are often treated as harmless, but they can inadvertently contain sensitive values if developers are not careful. Logging hygiene requires redacting secrets before they are written and disabling any echo of environment variables that may contain sensitive data. Without this discipline, logs can become gold mines for attackers, since they often persist long after other systems have been secured. By enforcing strict redaction and sanitization policies, organizations ensure that logs remain a tool for troubleshooting, not a liability waiting to be exploited. Even with preventative measures, mistakes happen, and secrets may slip into source history. Source history remediation is the process of finding and removing exposed values from repositories. It involves not just deleting the secrets from recent commits, but also revoking them to ensure they are no longer valid. Tools exist to rewrite histories and strip out sensitive content, but remediation must always be coupled with revocation. Otherwise, an attacker who already cloned the repository may still have access. This practice closes the loop on exposure, ensuring that the secret is both removed from the codebase and invalidated everywhere it might have been used. For more cyber-related content and books, please check out cyberauthor.me. Also, there are other prepcasts on cybersecurity and more at baremetalcyber.com. Injection pathways represent one of the most overlooked but highly dangerous areas of secret management. These pathways include configuration files, environment variables, command line flags, and metadata services provided by platforms such as cloud providers. Each of these channels is a potential doorway where a secret can be injected, either accidentally by developers or maliciously by attackers. For example, a cloud instance metadata service can provide temporary credentials to workloads, but if improperly exposed, those same credentials can be harvested by an attacker with network access. Likewise, a command line flag passed during startup might seem harmless, but in many systems, command line arguments are visible to other processes, effectively leaking the secret to anyone monitoring the system. Understanding where and how secrets flow into an application is the first step toward ensuring they remain under strict control. A related hazard emerges when templates collide during build or deployment. Many systems rely on template engines to define configurations, and these templates often accept user inputs or defaults. If those values are not carefully validated, a user input might overwrite a securely defined value with something less secure, or worse, expose a secret in a way that was never intended. Consider a deployment pipeline where a developer includes a placeholder for a database password, expecting it to be replaced by a secure retrieval system. If a default is accidentally used instead, the final build may embed the password directly into the configuration. This kind of collision often happens silently, making it critical for organizations to implement checks that verify template integrity before deployment completes. A safer design pattern to avoid embedding secrets directly is the use of parameterized connection strings and client configurations. Instead of writing a literal password into a database connection string, the string includes placeholders that are dynamically filled with credentials at runtime. For example, rather than user equals admin, password equals secret 123, the configuration specifies user equals $DBUSER, password equals $DBPASS, with the actual values pulled securely from a vault or orchestrator store. This ensures that no code artifact ever contains the literal credential. Beyond reducing risk, parameterization also improves flexibility, since different environments can supply different values without requiring developers to alter the codebase. It is a small but powerful shift in design that hardens systems against accidental exposure. Another safeguard comes from the practice of artifact inspection. This involves examining the final outputs of builds, such as container images, application layers, or compiled binaries, to confirm that secrets are absent. It is not enough to assume that because developers followed the right process, nothing slipped through. Automated inspection tools can search for recognizable patterns, validate that environment-specific secrets are not baked into images, and verify that archives or compressed packages do not contain sensitive files. Imagine a developer who accidentally added a secret to a temporary configuration file during testing. Without artifact inspection, that file might ride along into the production image and remain hidden until exploited. By baking inspection into the release process, organizations create one last filter that ensures secrets stay out of distributed assets. Even when secrets are delivered securely, what happens after they are used matters just as much. Zeroization is the practice of clearing secrets from memory in temporary storage once they are no longer needed. Without this, secrets can linger in system memory, disk caches, or swap files, waiting to be harvested by attackers or exposed through debugging tools. Zeroization can be as simple as overwriting variables in memory, or as complex as securely wiping temporary files created during execution. A useful analogy is shredding sensitive documents after use. You would not leave your tax returns lying around on a desk. Similarly, applications should not leave passwords or keys lying around in memory where they might be rediscovered later. Separation between environments is another cornerstone of secure secret management. Development, testing, and production each require different levels of access and therefore should never share the same secrets. Allowing production credentials in a development environment creates unnecessary risk because those environments often lack the same level of monitoring and hardening. Instead, each environment should use its own isolated secret store, scoped identities, and access controls. This separation ensures that even if a development system is compromised, attackers cannot leapfrog into production. It is much like using different bank accounts for household expenses and business operations. If one is compromised, the other remains safe. Clear boundaries reduce the blast radius of any potential exposure. Dynamic credentials provide yet another way to strengthen security by minimizing reuse. Instead of issuing a long-lived database password that is shared among all clients, a system can generate short-lived credentials on demand. Each request might produce a new username and password pair valid only for a few minutes, after which they expire automatically. Cloud platforms and modern database systems increasingly support this model, because it makes stolen credentials useless beyond a very short window. Imagine an airport issuing boarding passes that are valid only for the specific flight and time. Even if someone found an old boarding pass in the trash, it would no longer grant them access. Dynamic credentials transform secrets into temporary passes rather than permanent master keys. Mutual Transport Layer Security, or MTLS, represents another important evolution away from shared secrets. In MTLS, both the client and the server present digital certificates, and trust is established only if both sides verify each other. This model replaces the need for a shared API key or password, since the identity of each participant is cryptographically proven. Certificates can be managed centrally, rotated automatically, and bound to specific workloads. This makes it far harder for attackers to impersonate services or eavesdrop on communications. For example, in a microservices architecture, rather than having dozens of services share the same secret, each service presents its own certificate and verifies the others, ensuring trust is distributed and verifiable. Inadvertent exposures often happen through debugging and diagnostic practices. Remote debugging sessions, verbose logging, and automated crash dumps can all inadvertently capture sensitive data, including secrets. A developer trying to troubleshoot a failing authentication step might enable extra logging, only to discover later that the logs recorded the raw password. Similarly, a crash dump may include memory regions that contain API tokens. These practices highlight the importance of limiting diagnostic verbosity in production, as well as ensuring that sensitive values are redacted or excluded. Developers must balance the need for visibility during troubleshooting with the imperative to keep secrets safe, using sanitized logs and controlled debugging sessions as a compromise. When a secret does leak, organizations must respond quickly and systematically. Exposure response playbooks outline the exact steps to take: revoke the exposed credentials, rotate associated keys, search logs and systems for any signs of misuse, and notify stakeholders who might be affected. These playbooks work much like emergency drills, ensuring that everyone knows their role before a real incident occurs. Without them, response times can lag, and attackers may exploit the window of opportunity. A well-practiced playbook ensures that secrets are replaced, risks are contained, and lessons are integrated into future preventative measures. Policy enforcement has also become increasingly automated through the concept of policy as code. This involves writing security rules in a declarative format that can be executed by automation tools. For example, a policy may state that no infrastructure as code template can include a plain text password. Automated checks enforce this rule at every pull request or pipeline run, blocking violations before they enter the environment. By embedding policy into the development lifecycle, organizations create guardrails that developers cannot easily bypass. This helps shift security left, integrating it into the earliest stages of code creation rather than leaving it to audits after deployment. None of these practices work without people who understand them. Training programs are essential to ensure that developers, operators, and security staff all know how to handle secrets safely. These programs must go beyond abstract lectures, teaching specific patterns in the languages, frameworks, and build tools that teams actually use. For instance, showing a developer how to integrate a Python application with a vault has far more impact than simply warning about hard-coded credentials. By making training practical and directly applicable, organizations empower their teams to adopt secure habits naturally, reducing reliance on after-the-fact corrections. Metrics provide a way to measure whether secret management practices are working. Common metrics include time to revoke exposed credentials, the number of prevented commits flagged by secret scanners, and the success rate of rotation procedures. By tracking these indicators, organizations gain visibility into both their strengths and their weak spots. If rotations consistently fail or take too long, for example, it signals the need for process improvement. Metrics turn secret management from a vague aspiration into a quantifiable discipline, making it possible to demonstrate progress and accountability to stakeholders. Equally important is recognizing the anti-patterns bad practices that persist despite repeated warnings. Encoding a secret with base 64, for instance, is often mistaken for encryption, but it provides no security whatsoever. Sharing secrets casually in chat channels or documents leaves them exposed to anyone with access to those platforms. Storing secrets in unusual places, such as domain name system records, creates risks that are both unnecessary and difficult to monitor. Identifying and eliminating these anti-patterns is a key part of building a mature security culture because they represent shortcuts that undermine more robust systems. Finally, compliance requirements ensure that secret management is not just a best practice, but also a documented, verifiable process. Evidence may include vault policies that define access rules, logs showing when and how secrets were accessed, rotation records proving that credentials are regularly renewed, and exception approvals for unusual cases. These artifacts give auditors and regulators confidence that secrets are handled responsibly while also strengthening internal governance. The end result is a system where secret management is not left to chance, but is enforced by both technical controls and organizational accountability. In summary, secret-free code combined with identity-based retrieval and rapid rotation eliminates a major class of compromise paths. When secrets are not embedded in source or artifacts, when they are delivered dynamically through governed systems, and when they are renewed regularly, attackers lose one of their most powerful entry points. What remains is a development and runtime environment where credentials are treated as temporary, auditable, and tightly scoped resources rather than permanent vulnerabilities. This shift requires both cultural change and technical rigor, but it transforms secret management from a recurring headache into a strategic strength. Thanks for tuning in to the Bare Metal Cyber Prepcast, your trusted source for cybersecurity news and insights. Remember to subscribe at baremetalcyber.com so you never miss an update. And visit cyberauthor.me for best-selling cybersecurity books that equip you with expert knowledge. Until next time, stay secure and stay vigilant.